So when you consider the gamma decay process, unlike the beta or alpha decay process, this happens after, normally in general we can say this happens after beta decay process or along with the beta decay process. That is, in some cases, when you are having some beta decay, that doctor nucleus will not land up in the ground state. Okay. And in such cases it will be landing in some excited state, and later that excitation from the excited state it will go to the ground state by emission of gamma radiation. So normally this is a beta decay. But for example, in this case cesium, which is decaying into barium. So cesium, which is having 137 and 55 atomic number, and this is converting in or decaying into 137 of 56. Okay. So this is Z minus 1. So one proton is converting to what is that, neutron, right? 137 and 56. So this will be Z minus 1, right? This is Z minus 1. 56 means that it is Z minus 1. Okay, so that when this decay process happens, this is a beta decay process. Whether it is beta negative, whether so Z is 55 to 57. So Z becomes Z minus 1. What is this? One proton changing into neutron plus what is that? This will become. You check this. This is positive beta decay or negative beta decay, that you confirm. Okay. So because when this happens, this proton will change to neutron, right? And one positron should come. Then only it will, otherwise neutron to proton plus electron. Okay, I think this will be positive beta decay, right? I don't know whether you just take 56 means Z. Oh, sorry. This is 56. I did a mistake here. So this will be Z plus. Okay, this is 55 to 56. Okay, I thought it is some minus number. So this will be a negative beta decay. So in this particular case, the neutron is going to convert it into proton, and you are increased one proton number. That is why your atomic number is increased. So P plus electron plus an antineutron. Okay, whatever it is. So this decay process happened, and 5% of this process will happen in generally for 5% it will happen and into the ground state. That means that this beta decay happens and the barium will be in the ground state. Barium 137, 56. So about 5% of that reaction, it is directly going from this cesium to ground state of barium. But 95% of times it will go to the excited state with we have an half-life of some 2.55. I think this is 2.55 minutes. Okay. So this much of minutes it will be in this state. So it is an intermediate state. So it is an excited state, we can say. So this in here the barium will be in excited form, that is Ba star. We represented as barium in excited like this. So that excited state will after some t half time that will go into the ground state like this, as you can see. It will go to the ground state with emission of radiation, which is called as gamma radiation. Okay, this is what happens in the case of gamma emission. Similarly, if you consider the cobalt decay, also you can see that cobalt 60 with I don't know what is this number. What was that? We did it before, no? So just check that. I think it is 27, right? So this is 27, cobalt 60 and 27, that is in this level, that is decaying into actually this is nickel. This is nickel, it is 20, sorry, I should not write it there. So this is nickel 26. This is nickel 26 with the 60. Okay. So this is decaying into a state which is not the ground state, and there are different states here. And when it comes down, let's say that is landing up in this position, and when it comes down like this will cause emission of gamma radiation. Okay, this will cause emission of gamma radiation, or if you're having a direct landing, like if it is landed somewhere here, then also it has to move to the ground state, then this will also produce some gamma radiation. So this gamma radiation energy depends on the state energy. For example, in this case, this is having some 2.5 mega electron volt. This state which is having some kind of 2.15 mega electron volt. This is 2.15 mega electron volt. Okay, and this is having some 1.33 mega electron volt. Okay, so the difference between this is ground state. So the difference between these energy levels, what is that energy? That will be the energy of the gamma radiation which is coming out. Okay, and similarly here we have 2.5 minus 1.33 in this particular case. So that will give you around 1.17, something like that. You can calculate. This is 1.17 mega electron volt or something. So that is the energy of this gamma radiation. That is the difference between these energy levels. What is the energy that is associated with this gamma radiation that is coming out from this action? So, and if you consider one positive beta decay process like this, then in that particular case, we have the sodium. In this particular case, we have the sodium, which is Na2211, which is going through a beta positive decay and landing up in some excited state. So this is neon in excited state. It is going to be to the ground state with emission of gamma radiation that coming out. Okay, this gamma radiation which is coming out, and with 1.27 mega electron volt. So that is the radiation energy, or the radiation energy of this particular gamma. And when it comes from the excited state to this ground state of the neon, 1022, right? Okay. So that is what will happen in these reactions. When you are having beta plus decay, you will be having a reduced Z number. So 94% of time this will happen. 94% of time of beta plus decay will happen like this, and some 5% this will happen through electron capture. So what that means, if this neon, which is in excitation cell, so that sodium is decaying into this excited state of neon, it can be through beta plus decay, or it can be through electron capture. Okay, both of these are possible for the sodium to neon decay processes. So it can be through electron capture, it can be through beta plus decay. Both ways you will end up into the same mass number, and you will be having atomic number which is reduced by 1 in both cases, with positive beta decay and negative beta decay. So in that particular case, we can have 95 or 94, around 95 times. This is 95 and 95, almost 95 percentage of time it will follow that beta B post decay, and 5 percentage of those reactions will be through uh, electron capture. Okay, 95 percentage through beta plus decay and 5 percentage through electron capture. So both these are possible in this particular decay from sodium to neon. So when it follows the beta plus decay, it end up in the excited state of neon. Then from that portion, it will come to the ground state of neon by emission of energy, which is equivalent to this two difference of these two states, and that will be coming out as gamma radiation. So this is the so these are the sources or origin of gamma radiations, how the gamma radiations are coming. Okay. Now, if you consider the energy of gamma radiation, we can say that the low energy gamma radiation, low energy gamma radiations are, or gamma rays are, equivalent or comparable to high energy X-rays. Okay, if you consider X-rays, which is in the electromagnetic spectrum, if you consider gamma ray also an electromagnetic radiation, which is photons. X-rays also electromagnetic radiation, which is also photon. Beta and gamma particles, beta and alpha particles are particles which are not electromagnetic radiation. So you remember that. So this decay process, electron, it is beta particle, alpha particle decay, which are particle decay processes. But gamma decay is an electromagnetic radiation which is coming out, or the photons which are coming out. So it is similar to X-rays, X-ray, which X-rays also photons or electromagnetic radiations. Similarly, gamma also photons, or they are the electromagnetic radiations with comparable energy. So what we can say, the low energy gamma radiation, low energy gamma photons are comparable with the high energy X-rays. Or if you say the frequency spectrum, okay, let's say this is the X-ray range, okay, X-rays range. And if you consider sorry, this in this case I should write X-ray. If you consider that frequency, if you consider frequency, I should write first X-ray here. So this portion will be X-rays, and this portion will be gamma if you consider frequency, and frequency is increasing in this direction. So higher frequency X-rays and lower frequency gamma radiations are comparable. Okay, this is the X-ray radiation range. This is the gamma radiation range. So if you consider this particular point, then we can say that high X-ray frequency, higher energy X-rays are comparable with the gamma radiation. Okay, so that's that story, that the high X-ray, high energy X-rays are comparable with the gamma radiation, and it is also similar because they are photons, they are X-rays. These are electromagnetic radiation. Both of them are electromagnetic radiation. Both of them are photons. They are similar, but their origins are different. X-rays comes when you are having that electrons excitation or de-excitation happens. For example, if you consider the atom with Bohr model of atom for an easy explanation. So if you consider these are the orbits, and if you say these are the shells and K, L, M, and like that, and if you have somehow you knocked out one particular electron from this shell, one electron will come to this part and it will emit some radiation that is coming as your X, in this particular case Kx radiation, which is coming out because it is reaching in the final state of K shell. So this is the origin of the X-rays, which is coming from the de-excitation of those electrons which is revolving around the nucleus. So if you give enough energy to the inner shell electron, that electron will be knocked out from that shell, and an additional electron from the higher orbit or L shell, for in this case, it will come to that position that is vacant, and corresponding energy that is in between these two in these two orbits, that how much energy is that, that will be emitted in the form of electromagnetic radiation, and that is called as X-rays. And in this particular case, they are K X-rays. And if you take the another level, and it is landing into the L, then you will be having L X-rays and all those things. So if you are having electrons which is de-exciting in orbits, you will get the X-rays. But in case of gamma rays comes from the excitation of nucleus. Okay, it is not from electron, which is coming from nucleus. For the case of, as I said in the previous case, when, for example, in the case of sodium, which is going to neon, this neon end up in the excited state. It will not be in the ground state. This will come into the ground state by emission of gamma radiation. So de-excitation of the nucleus will give you the gamma radiation, but de-excitation of electrons, or the electrons excitation, de-excitation, will give you the X-rays. Okay, so one is through electrons, and the other one is through nucleus. That is different. So they are differ by their origin, even though they are photons, or they are electromagnetic radiation. Their origin is different. Okay, so then now if we consider electromagnetic radiation when produced, if you consider any electromagnetic radiation, they will be produced by an oscillating charge or through a current which is varying with time. So these are the two mechanisms. Normally, if you are having oscillating charge, that can produce electromagnetic radiation. In case of antenna, we can say that the dipole oscillations that make the signal, uh, these things are, I don't know whether you're familiar, if you consider the antenna or tower or something, and then there will be the dipoles or quadrupoles or the multipoles in there. The charges are there, that charges oscillate, that will produce electromagnetic radiation that will be received in your home and whatever it is. Okay, so that is coming. So this is through oscillation of charges you can produce electromagnetic radiations, or you can have you can also produce by varying current with time. So that are the source of electromagnetic radiation. So these changes, again, we can classify into as monopole, dipole, or quadrupole, or any multipole radiations. It depends on what kind of charges you are having. If you are having monopoles, then you will be having some monopole radiation, but that does not exist. That is another matter. But if you're having, normally if it starts with a dipole, if you're having a dipole, which means that you will be having two charges, two monopoles that are separated some distance and all those things you already know. So if that dipole is oscillating, then that will produce some electric field, electromagnetic radiation. Then that kind of radiation is called as dipole radiation, electric dipole radiation, if it is electric. If it is magnetic dipole, then it is called as magnetic dipole radiation. Similarly, if you are having quadrupole, what is quadrupole? If you are having two dipoles, or if you are having four monopoles or four charges, charges means that the charge distributions for similar kind of charge distribution, then you can have a quadrupole. And that quadrupole, if that quadrupole is oscillating, then that can produce electromagnetic radiation that is called as quadrupole electromagnetic radiation. If it is electric quadrupole, it is called as electric quadrupole radiation. If it is magnetic, then it is called as magnetic quadrupole radiation. So it depends on what kind of charge distribution or magnetic distribution that you are having, or what kind of system you are having, whether it is monopole, dipole, quadrupole, or any other higher dimensions. And depends on that, it will be different, but we can categorize or classify them, this radiation, accordingly, what kind of charges that that is oscillating in that particular source. So if you consider a pure monopole, consider a pure monopole condition, then that will be monopole, which is nothing but a spherical charge distribution. If you consider a sphere, and if you look at that sphere very far, from very far, they can say that that is a monopole. And it does not mean that it's a single charge, but it is a charge distribution. But if you are very far from that charge distribution, you can see that as a monopole, which is confined in particular region. If you consider dipole, when you are having no with monopole, if the monopole moment is zero, then you have dipole, which is existing, which is having some field of that we expressed here, p equal to p, that is unit vector p, 2 cos theta plus that is theta r cap. So I can say this p nothing but p vector with 2 cos theta r cap plus this you already know these things. These are fundamentals of dipole and quadrupole. All those things you must have learned from electrodynamics. So for pi epsilon 0, this is r cube or something. So you can see that with quadrupole we have a different charge distribution. With dipole we have a different charge distribution. In associated with that, we will be having different kind of field distribution, electromagnetic fields, when these multipoles oscillates. Okay, so accordingly, we can say that these kind of radiations are associated with this dipoles, quadrupole, or any other kind of polarities. I mean multipoles. So if you consider this dipole or any other polarities, I didn't find it out. If you consider dipole moment, which is oscillating, then we call it as a dipole radiation. So if you, which means that I hope you understood this radiation part. It is basically coming from electrodynamics. You know, you might have studied that if you are having a charge, if this charge is moving, this when this moves, it will produce some radiation which comes out. Where similarly, if you are having oscillating charges, that radiation will come out. That will produce some electromagnetic radiation. So that is the concept that we have taken here, and there is some relation also. You might have studied that in your electrodynamic course. So if you are having some dipole like this, they are separated with some distance, some charge distributions, minus n plus q. And if these are oscillating in some fashion, they will produce some electromagnetic radiation. If you are having quadrupole or any other multipole, also we will be having this kind of electromagnetic radiation with oscillation of that charges. Okay, these are the basics of the electromagnetic radiation for X-rays as well as in the case of gamma rays or whatever it is. So if it is from dipole, then we call it as electric dipole transition, which means that if it is from electric charges and the distribution is dipole, then we call it as electric dipole transition. If it is magnetic, and then, for example, if you are having two polarities, that is the magnetic dipole, if you consider, then if they are oscillating, then you can have magnetic dipole radiation. So you have some same kind of phenomena with the magnetic dipole. So then it is called as magnetic dipole radiation. And if you consider any other higher order multiples, then correspondingly we can term it as electric corresponding, for example, quadrupole, and then it is electric quadrupole radiation, etc. Okay. So if you consider now the case with the gamma rays, okay, if you consider with the gamma rays, these radiation also classified in the same way as we discussed. Okay, but when you consider the monopole moment, if you consider the monopole moment, this does not produce radiation. Okay, for example, if you are having a spherical charge distribution, so it is spherical in nature, and if you look at it from very far distance, and if you see this spherical charge distribution is oscillating, even if it is oscillating, you cannot find any change in that because of the spherical nature. So it will not produce any electric field. while oscillating. Oscillating means it has to move back and forth, but that will not change any of its structure, and it will not change it will not produce any electromagnetic radiation. So basically, monopole moments they are that do not produce any electromagnetic radiation because of their spherical charge distribution. So we cannot get electromagnetic radiation from monopole. So it all starts from dipole radiation, basically. Okay. So the first radiation that we have to consider from dipole, whether it is electric dipole or magnetic dipole, it depends. But we start from dipole, quadrupole, and octopole, etc. So when we consider this, when the photon which is coming out from after beta decay, that means if you consider the same case, for example, sodium going to neon with excited state coming to ground state with gamma emission. So these photons, these are the gamma radiation, these are the photons, electromagnetic radiation associated with the fundamental quanta of energy, which are photons. So the particles associated with electromagnetic radiation, which are photons. And these photons will be having some angular momentum. This is also associated with angular momentum, and that is represented by capital L. Okay. So if these radiations which is coming out, which are photons, which are having angular momentum L, for example, the angular momentum L value equal to 1, L value equal to 2, etc., then the corresponding radiation we can call it as electric dipole radiation of E1 type. Okay, electric quadrupole radiation, that is E2, and electric what is that, octopole and all those things we can say, and that will be E3, etc. So it will go like this. If it is magnetic, then it will be M1, M2, M3 type, which means that if the angular momentum of that particular photon will be 1, if L equal to 1, then it is for dipole radiation, and if L equal to 2, which is quadrupole radiation, etc. So the angular momentum of these photons which is coming out as a gamma radiation, which will determine what kind of radiation it is, whether it is a dipole or a quadrupole radiation, etc., will be determined by the L value or the angular momentum of that particular gamma, this particular gamma radiation which is coming out. That is that has to be noticed. So when you consider the case when you are having an angular momentum of the initial nuclei, which is Ji, that is the first nuclei. In this particular case, we have a sodium, that is the angular momentum of sodium. So, which means that the angular momentum of the initial nuclei, that is the parent nuclei, that is represented as Ji, and the final state angular momentum, that is the angular momentum of neon or the daughter nuclei, that is Jf. Then the photon has to follow this particular equation, or it has an angular momentum L in such a way that Ji equal to Jf plus L. Okay. Okay. So let's consider a gamma decay process where we have one X nucleus which is in the excited state and it is coming to the ground state. Okay. So in this particular case, this excited state is having some higher energy, which is not in ground state. So there is some excess energy. That excess energy has to be transferred, and that will be transferred in the form of gamma radiation. And this gamma radiation, when it comes out, these gamma radiations are photons, and these photons are associated with some angular momentum L. Okay. So if you consider this scenario, then your excited state is associated also, this nucleus in excited state, also associated with some angular momentum. Let's say it is Ji, and the ground state nucleus, which is also associated with some angular momentum, that is J final. Then we can say that to conserve the angular momentum, the initial angular momentum should be equal to the final angular momentum, and the final angular momentum is nothing but the addition or the sum of final state nucleus angular momentum and the photon angular momentum. Okay, so this is the condition for the angular momentum conservation. So initial angular momentum, whatever it is, which should be equal to the final state of the nucleus angular momentum of the ground state nucleus, plus the photon angular momentum. Okay, so from this condition, we can say that if you take Jf into the other side, we can say Ji minus Jf equal to L, or we can, in general, we can say this should be equal to or less than the L value. In other ways, we can say Ji plus Jf. So this should be in magnitude. There is no negative. Okay. So Ji plus Jf, if you take, this should be greater than or equal to L value. That you can give some, for example, Jf, for example, in the case of Ji equal to 1 and Jf equal to 0, then L should have more than that. Then only you can have this kind of condition, that you can give some numbers for that and you can measure these conditions. Okay, these two conditions. So from that, we can say that L value should be in between Ji minus Jf and Ji plus Jf, or which should be equal to L value. So in the momentum conservation, we derive that the L value lies in between Ji minus Jf or Ji plus Jf, or that L value should be equal to these two values when they are equal. Okay. So, and also when you consider the parity of the initial and final state, which means that the parity of the excited state nuclei and the ground state nuclei. So, which means that parity of initial state, which is nothing but parity of the excited state nuclei, and parity of final state is nothing but parity of the ground state nuclei, that is X, let's say. Okay, so that should be like this parity of the ground state nuclei should be equal to parity of the excited state nuclei times minus 1 to the power L. If it is following this kind of condition, then it is called as electric multipole transition. This is for electric multipole transition. And if the parity of the ground state nuclei, that is parity F pi F, that is final parity, that is equal to initial parity times minus 1 to the power L plus 1, minus 1 to the power L plus 1. So here L plus 1. If it is following this condition, then it is called as a magnetic multipole transition. It is called as magnetic type multipole transition, which means that the radiation which is coming out, that is gamma radiation which is coming out, can be from electric multipole transition or magnetic multipole transition, that we already discussed. So how we can determine this, whether it is electric or whether it is from magnetic, that we have to look the parity of the excited state nuclei and ground state nuclei. And when it forms this condition, the excited nuclei and the ground state nuclei is having this kind of condition for their parity, then we can say that it is coming from the electric part or the electric multipole transition. The radiation is coming out. Or we can, if it is following the second condition, that is this one, if it is following this particular case, then we can say that the electromagnetic radiation which is coming out is produced from a magnetic multipole transition. So some magnetic multipole is oscillating, and that produces that kind of gamma radiation. Okay, so that is about the parity of this. How we can determine the electric, whether it is electric multipole or whether it is magnetic multipole from the parity analysis. If you consider this particular example, this is for germanium, which is having two excited state here with a different angular momentum and parity. Now, if you consider this particular case, when you are having this 0 plus to 0 plus transition, okay, that is one of the transition which is possible in this particular case. That is this one. So the from the excited state to the ground state, it's from 0 plus to 0 plus to the 0 plus transition. So if you consider that particular transition, then our Ji equal to, what is that Ji? That is the initial state angular momentum that is in the excited state now. So this is your initial state. This is your, so from initial state, the angular momentum is here we represented as J pi, which means that the angular momentum equal to J, which is 0, and parity is positive. Okay, so Ji equal to 0, that is the initial state angular momentum, and Jf is the final state angular momentum, which is equal to also 0, that is here in the ground state that we can get from here. From that we can say Ji minus Jf, and this should be equal to or less than or equal to L, which is less than or equal to Ji plus Jf, and this should be in magnitude. There is no negative values for Js. So from this we can say this is 0 because Ji and Jf are 0. So this is 0, which is less than or equal to L, which is less than or equal to 0. This implies the L value should be equal to 0. Okay. So what kind of radiation that can produce? When L equal to 0, we said L equal to 0, which is for monopole, at corresponding angular momentum is for monopole, and this will not produce any radiation. There is no radiation for monopole. So we will start from L equal to 1, which is corresponding to the dipole radiation, dipole transition, and which will produce the radiations. So for L equal to 0, there is no radiation which will come out. So for 0 plus to 0 plus transitions, we do not have L value which is higher than 0, or the L value in such kind of transition will be always 0. So in that kind of case, we will not be having any electromagnetic radiation. Okay. Then similarly, if you consider any such kind of radiation, not only for this case, if you are having 0 plus to 0 plus radiation transition from excited to say state to ground state, or let's say if you are having some other transition which will give you L equal to 0, then that kind of transition will result in monopole, and that will not give you radiation, which means that there is no gamma radiation produced in this particular kind of transition. So we can say that how this will not produce electro gamma radiation. Gamma radiations will not produce by this. So how this particular nucleus will then give this energy or release this energy? That is a question. So if you consider in this particular case 0 plus, this is in the excited state. Okay, this is in the ground state. So this excited state, somehow it reached in the ground state. How it is reaching? That is the question. It is not giving any radiation because the L value equal to 0. It cannot produce any electromagnetic radiation. So then what happened is an important or interesting thing that if you are having nucleus in such kind of transition, suppose then you consider that the Bohr model of atom, that you will be having one electrons which are revolving around this nucleus like this. And if you consider this kind of transition, that is from, that will give you L value which is equal to 0, then that will not produce any radiation. In such cases, this particular nucleus which is in excited state, and that will give its excess energy to this the closest, okay, to this closest electron, and that electron absorb that energy and that can come out from this atom, and this nucleus will release, or it will transfer that excess energy to that electron, and it will become ground state. It will comes to the ground state, or it will become stable. And this electron that received that energy can come out from the atom. And this particular process is called as internal conversion. This particular process is called as internal conversion, or IC. Okay. And this can be used as an electron source and those things in some experiments. You can use it as electron source, because from the internal conversion we get electrons which is coming out, and such kind of nucleus we can use for as an electron source. Okay, so this is the process, internal conversion, which will happen when you are having your L value equal to 0. Normally it will happen when you are having L value equal to 0, and that excess energy is transferred into electron, and the electron will come out. So it is transferring into the nearest electron. That means the first orbit only it will transfer, or then if that electron is coming out and other things. Okay, so that is the process will happen in this particular scenario, in this particular case. Okay. And in the second case, when you are having this 2+ state, that is also an higher energy state, or the nucleus is in the excited state. So when it comes down to the ground state like this, from this state, okay, so that is from 2+ to 2+ state to 0+ state. So your Ji value is equal to 2, and Jf value equal to 0. See? And there is no parity change in this case also. There is no parity in here also. So we can say that Ji minus Jf, and if you take all those values, then you say that 2 will be, which is less than, okay, which should be less than or equal to L, and it should be less than or equal to 2, and which will give you L value which is equal to 2. So what is that L value equal to 2 means? This is the quadrupole radiation. Okay, from this itself you can say this is quadrupole, because L equal to 2. L equal to 1, then it is dipole. Similarly, the series will go. So L equal to 2, now it is a quadrupole transition. Electromagnetic radiation is possible because L equal to 2. Gamma radiation is possible. So L equal to 2 will give you quadrupole transition. But what kind of transition it is, whether it is electric or magnetic, that we have to look by considering the parity of initial and final states. So we have a plus parity in the initial state, we have a plus parity in the final state, which means that there is no parity change. Okay, so if you consider minus that final and initial states parities, so we have pi f and pi I. So we have pi I, which is equal to positive parity, that is +1. Okay, pi f also we have +1. Then we have to consider that equations, that pi I in the first case, for the case of electric transition, electric dipole, electric multipole transitions, we had equations which is dependent on -1 to the power L. Okay, it is independent of that. It is not L +1. So I think it should be n pi I. This should be equal to times -1 to the power L. All right. This is pi f. Is this right? Pi f equal to pi I -1 all raised to L, or pi I equal to pi f.
ഇതൊക്കെ ഇന്നലെ സാർ എടുത്തതല്ലേ?
അന്നേരം തന്നെയാണ്. So this whether this is right, pi I equal to pi f into minus 1 over raised to L, or pi f equal to pi I. What is that? ആരില്ല ഇവിടെ? The answer വരാത്ത pi I equal to pi f ആണോ pi f equal to pi I ആണ്? ഇങ്ങനെ വരിക ഗാമ റേഡിയേഷന്റെ പോയോ?
pi f is equal to pi I minus 1 raised to L അല്ലേ? L 2 pi f is equal to pi I.
Okay, so in this particular case, if you substitute that, then pi I equal to plus 1. Okay, then pi I is plus 1 minus 1, L equal to 2, then you'll get L square, that minus 1 all square, then this will give you plus 1. So your pi f equal to plus 1 and your pi I also plus 1, so you'll get these conditions. Now if you substitute same value for the second case, so this is for electric case. So for electric it is okay. For electric case it is okay. If you consider for magnetic case, pi f equal to pi I minus 1 to the power L plus 1, then if you give that, pi I equal to plus 1 and minus 1 to the power L plus 1, that is 2 plus 1 will be giving you 3. So this will give you plus 1 minus 1 to the power cube, that will result in minus 1. So your pi f now is minus 1 and pi initial is plus 1 that we given here. So that is difference. That is different. So initial and final parities are different here. That is not the case when you consider this transition. You have both cases, your parity is same, both are plus. So this is not right. So in the case of magnetic transition, this will not hold. So this is not correct with the given transition. So we can say that this is quadrupole transition from L equal to 2. This is electric transition under this parity conditions. Then we can say the total transition as electric. This is electric quadrupole transition. This particular transition means that electric quadrupole transition. That means that the radiation, that is the gamma radiation, which is coming from oscillation of electric quadrupoles. Okay, that is the meaning. So it is coming from electric quadrupole. That's why we call it as electric quadrupole transitions. Okay. Now, if you consider another example, okay. Before that, we have another term, that is the conversion coefficient. Even if you consider this particular example, that is from 2 plus to 0 plus, okay, from 2 plus to 0 plus, there is still chance that this transition can occur through internal conversion, because that excess energy also can be converted into to the electron, and that electron can come out from the orbit. So that is also possible. So along with the gamma radiation, there is still probability or possibility for electron this internal conversion that can happen. So how much is that probability? That will be given by this conversion coefficient. So I don't know what is this cursor. Okay. So this conversion coefficient, which is defined as probability of internal conversion to probability of gamma decay. So if the probability of internal conversion is larger, then the conversion coefficient will be larger, and that particular transition from the excited state to the ground state will happen through internal conversion. When that conversion coefficient is less, and then we can have the probability for gamma decay is larger, which means that the gamma decay domain is. So by using this equation, or by considering gamma conversion coefficients, this conversion coefficient, depending on this value, we can say the probability of internal conversion is higher or the probability of gamma decay is higher for any gamma decay process like this one. So there is two possibilities, one through internal conversion or through gamma decay. So which will dominate, that will be given by the conversion coefficient. You calculate what is the probability of internal conversion, what is the probability of gamma decay, take the ratio between them. That will give you some constant value, that coefficient value. And that will be, if it is larger, that means that the probability of internal conversion is large. Or if it is smaller, then probability for gamma decay is large. So that is the internal conversion coefficients that we have to. So for example, the probability of gamma decay is maximum. That means that probability is equal to 1. And probability of internal conversion equal to, let's say, probability of gamma decay is maximum. That is equal to 1 if you put that value. Then probability of internal conversion, that should be 0 because this is having maximum probability. Then that will give you 0 by 1, which is having a value of 0 for this conversion coefficient, which means that the internal conversion is very rarely can occur. Or if you consider some higher value for internal conversion, let's say some 0.8, and you have zero point 0.2 of probability in for gamma, then we can say that zero point 0.8 by zero point 0.2, which will give you some value that is correspond to that coefficient. And from that you can say the conversion coefficient is larger and internal conversion is possible. Internal conversion is higher, having some higher probability. Okay, so from that conversion coefficient, you can calculate or you can have some estimate of which kind of actions or operations mechanism which will happen in that particular case, whether it is internal conversion or gamma decay. Okay. So now if you consider another example for this gamma decay processes, how it is happening, we can. Okay, in this case, 1 by 2, that spin of the excited state, which is 1 by 2 minus, and the ground state we have 9 by 2 plus. Okay, from this we can say that ji, that value in initial state spin or the angular momentum value, which is 1 by 2, and jf having an angular momentum of 9 by 2. Okay, so if you take jf ji minus jf, then you will get 8 by 2, that is 9 by 9 minus 1, that is of course it is minus is ignored or it is removed. So 9 minus 1, 8 by 2 will give you 4, that is the ji minus jf value. And ji plus jf you will get 5, that is 9 plus 1 by 2, that will give you 5. So your condition will be like it should be in between 4 in 4 and 5. Okay. So let's put it like this. I think it's 5. So L can have values. L can have values 4 and 5. Both are possible. Okay. Because L equal to 4 in this side, L equal to 5 in the other side. So you have L equal to 4 and 5 as your angular momentum corresponds to that photons. Then there is a parity change, right? Because your 1 by 2, that initial state is having minus 1 parity and the final state is having plus parity, that is 1 by 2 minus and 9 by 2 plus, that you can see from here. Okay, so when this when this nucleus coming from this excited state to the ground state, from this state with 1 by 2 and minus parity to 9 by 2 and plus parity. So if you consider that case, then L is equal to 4. Let's say first case L equal to 4. Then it has to be magnetic type. Okay, it has to be magnetic type, which means that M4 is the possibility. How it is? It can be magnetic type because there should be a change in parity. So your pi F equal to pi I. If you take minus 1 all to power L, If L is even, there is no parity change. Remember that. For this case, L equal to 4, then there is no parity change, which means that you will get same value, or you can do this also. This will be minus 1 to the power 4. This will give you pi I. So that pi f equal to pi I, which means this is not valid. You can get this pi f equal to pi I here, but that is not the case here, right? Because your parity is negative initially, then it is positive. So it should be different. So this is for electric case. So electric will not go. Electric is not valid. Now we have to go for the other case for magnetic, minus 1 all to the power L plus 1. Then you will get pi I. If this is odd, then it means that there is parity change for quick calculations. So L plus 1 is 4 plus 1 is 5. So this will give you minus pi I. Okay, so there is a change in parity. So this holds. So magnetic, which will be okay. So this is magnetic type. This is magnetic type because of L equal to 4. So this is M4 type of transition. We can say M4 because in general we write it as AL or M4, sorry, ML. So this is E for electric and L for the angular momentum of that photon, and M for magnetic, L is for that same angular momentum of that photon. So if you consider similarly for L equal to 5, if you consider that value is L equal to 5, okay, then it has to be electric type, as that you can get very easily because 5 is odd. 5 is odd number. Okay, then if you need that parity change, it has to be odd L value. If odd L value, then there will be parity change for electric case. Okay, if it is even, then there will not be any parity change for electric case. Okay, so since it is odd, then there is parity change, and our example is also having a parity change. So it should be electric, or you can substitute this L equal to 5 in this condition, then you can verify that it is changing parity, then it is associated with that electric. And if you submit that here, then L plus 1 will become 6, and there will not be any change in parity, so it is not magnetic in this case when L equal to 5. So E5 is also possible. It can be M4 or E5. Both are possible because the gamma photons which is coming out is having both angular momentum 4 and 5. The possibilities are 4 and 5. And if you calculate for whether it is magnetic or electric, M4 and E5 are possible. Okay, those are the possibilities. And then if you look further, if different multipolarities are possible, okay, it is important, different multipolarities are possible, then probability of decay through lower multipole transition will be higher. Okay, which means that if you are having L value which is different, and that is possible, so the outcoming gamma photons are having different L values, number of L values, then those L value which is having smallest or the lower order, that is the lower L value, that transition has more probability. Okay, so let's say L, in this case L equal to 4 and L equal to 5. So if you consider any number of these L values, which one comes the smallest, then this particular order of now if you consider that case, we can in general we can say that the probability with L plus 1 of order, that is the for angular momentum of that photon, and if you divide that probability with the transition of angular momentum L, with angular momentum L, which will be approximately equal to 10 raised to minus 5, which means that when the order of that transition change by 1, your probability is change in the order of 10 raised to 5. Okay. Then your probability changes with the 10 raised to minus 5. Which probability with L will be equal to 10 to the power 5 order of probability to the order of L plus 1. Okay, so that is about the different cases when you are having different L values when you consider. And similarly, if you consider for electric and magnetic probabilities in this case, okay, whether if you are having electric and magnetic both are possible, then in such cases, the probability for electric transition to the probability of magnetic transition will give you almost 10 to the power 2, which means that electric probability is higher as compared to magnetic probability in the order of 10 raised to 2. So we can say that probability through will be equal to 10 to the power 2 times probability through magnetic. So I'll say probability to L is 10 to the power 2 times probability to through ml. Okay. So from by using these kind of values for probabilities, by using these two equations, we can say from this at this point we are having L equal to 4 and 5. Okay, there is no higher terms. So L equal to 4 and 5. So from that we can say 4 is the smallest order. So that is having higher probability, which is 10 raised to 5 times more than the order 5. Okay. And then we analyze that which one, whether electric or magnetic. So when you consider that electric is having 10 to the power 2 probability of magnetic. So in that particular case, if you consider these two, okay, M4, M4, there are two things, M4. So when you consider M4, this is a little tricky. So M4 means that, what is that? M4 means that magnetic, which will give you 10 raised to minus 2 as compared to electric. And then you have 4 here. 4 means you will get a higher probability, that is 10 raised to 5. And if you consider another one, E5, that is E5, electric, which will give you advantage of 10 to the power 2 of the probability. And the 5, which is larger than 4 by an order of 1, then that will give you a disadvantage that with order of minus 5. So this is approximately equal to some 10 to the power 3. Okay, in both cases it will give you 10 raised to minus 3. So you have to choose the fourth one in particular case. In this particular case we cannot say this. This will come as, okay, this is minus 5. Okay, this will give you, okay, this also will give you the same result, I think. So this will give you 10 to the power 3 here, right? And this will give you something. So here you have E, that is 10 square. Okay, this will give you minus 5 here, right? So in this particular case, you will be having 10 raised to minus 5 and 10 square. This will give you 10 raised to minus 3. So the probability go high for this. So from that, we can conclude that this particular M4 type is the M4 type is the corresponding transition which will happen in this particular case when you are having the transition from 2 plus to 0 plus in germanium. Okay, that is through M4 type transition. That means that it will be through magnetic transition with order of 4. So that's how we calculate the gamma radiation, its properties, or whether it is coming from electric or magnetic, or the order of that transition, all those things that we can calculate from these equations. Okay, hope. There is one more thing I have to say in this gamma decay process. So it is called as resonant absorption. I didn't include it in there. Or we can say that it is recoil-less nucleus. We can also say it like that for resonant absorption or whatever it is. So first I will explain that. Let's say if you are having nucleus which is having this gamma decay process. Okay, so let's consider there is a nucleus which is in the excited state. Okay, so this is your excited state and this is your ground state, and this is where the nucleus is now, let's say, and this nucleus is going through that gamma decay, which is becoming a stable nuclei. Okay, so that will come like this. Now its position is in the ground state, and the nucleus is this. Gamma radiation goes in this direction. The nucleus move a little bit through the recoil, and that is velocity. By the recoil effect, the nucleus will move a little bit, and the gamma radiation will go in this direction. Okay, so this is the excited state, and it is coming from the excited state to the ground state here. And see from here, it's coming to the ground state here. Okay, so by the release of that gamma radiations. So this is this velocity is coming from because of that recoil effect of that nucleus. When the gamma goes in one direction, there is some momentum which exert on that nucleus by the gamma radiation that will cause some recoil effect of the nucleus. Okay, to conserve that momentum, and so that velocity associated with this recoil effect. Now, if you consider this difference, if you consider this energy difference as E0, this is E0, then we can say that this E0 must be equal to this E0 must be equal to E gamma, that is the gamma radiation energy which is coming out of this decay process, plus energy of gamma radiation, that is E gamma, plus that recoil energy, that is P square by 2m, and this P is associated with the nucleus, that is momentum of the nucleus, by 2 times m. That is the kinetic energy which is associated with this recoil effect. That is where a little bit the nucleus will move through the recoil effect. So corresponding kinetic energy is of that nucleus is P square by 2m. Okay, so this m is nothing but the mass of neutron or proton which is inside that nucleus. Okay, so that is the case. So here, that E0, that is energy difference which will be used for this gamma radiation and recoil effect of this nucleus. Now, if you consider the radiation's momentum, okay, let's say initially the nucleus is at rest. Let's say, or if initially the nucleus is at rest, that implies that momentum should be conserved. From that, we can say that the momentum of the gamma particle which is going out should be equal to that of nucleus. Then we can say that P gamma should be equal to nucleus when you are having the excited nucleus which is at rest. Uh, okay, you already know this. So this is the excited nucleus. So when it release the gamma radiation in one side, the nucleus will move in the other side in some velocity with some velocity. It will be like a recoiling effect only. That is not moving very far. Okay. So, but the momentum should be conserved and it should be moving in the opposite direction, and that will cancel the momentum of the photon. And because initially the excited nucleus was at rest, so total momentum should be balanced. So initially, the for excited state nuclei, for example, X star will become X plus gamma. Then this momentum is zero because it is at rest. Then this should also be zero. So one should be minus P nucleus and plus the gamma which is going. That should be P gamma. So when you take this inside this side, and it will be equal. Okay, so that means this negative is direction. Okay, so that means that P gamma should be equal to P nucleus. From that we know, but P gamma which will be equal to E gamma by C. Okay, energy of that gamma by C. This I will not explain because energy by C is your momentum that you know. Okay, so from that we can say, which implies that P gamma will be equal to E nu E gamma by E, which will be equal to P nucleus. Now you substitute that P nucleus value here, so you can say this is 1 and this is 2, all those things that you required. So substituting 2 in 1 will give you E0 plus E gamma. That will be sorry, E0 will be equal to, this is E0 will be equal to E0 E gamma plus E gamma plus P nucleus. You substitute that E gamma, this one. So this will give you E gamma square, right, by 2 m. So okay, so there is C also, C square. C square is E gamma square by C square. So that will give you E gamma square by 2mc square. Now it is not that much. The energy of the gamma radiation and this gap is not that much different, because most of the energy will be carried out by the gamma radiation. So if you compare the energy of gamma radiation which is going out and the energy difference between the excited state and ground state, so that is almost equal. That is E0, that is the energy difference between the excited and ground state. This is almost equal to E gamma. There is no much difference, and that small fraction of energy is taken away by the nucleus, and that is for recoil effect. Okay, so we can approximate E0, which is almost equal to that of E gamma, which is coming out, that the gamma particle which is coming out. That we can say that, but E gamma is E0 is approximately equal to E gamma, which will give you this equation, uh, which can be replaced as E gamma. Okay, actually we have to find out what is the value of E gamma from here. This implies E gamma will be equal to E0 minus E gamma divided by 2mc square. You can keep this equation, or you can uh, assume this condition, and you can give that E gamma will be equal to this E0 minus E0 divided by 2mc square. Why? Because E gamma is not that much different from the E0, that is the energy difference between the excited and the ground state. Okay, under that condition, you can have that equation. So the gamma photons that is coming out, that having some energy which is less than the energy of the level difference by E0 by 2mc square. Okay, so from this we can say that the gamma photons which are coming out has an energy difference of, what is that, E0 by 2 mc square from the energy separation. We can say energy separation or energy level difference. I should say energy level difference. It is better. That energy level difference is nothing but the excited energy level difference. And this energy level difference is nothing but the excited energy state to minus ground state energy, that energy difference. So from that, it is just that's why it is this equation is given by E gamma equal to E0 minus E0 by 2 mc square. So from that energy difference, it is differ by this much of an amount, E0 by 2 mc square. Okay, so if you plot that in a figure, then we can say that if you say this is that energy line, and this is your E0, that is the energy difference between those states, then your gamma radiation which is coming out will be somewhere here. Okay, so there will be a fine width because of the Doppler effect and uncertainty principle, all those things. We will not get a fine a straight line or a peak here. So there will be some width for this line, this particular line. So this is your E0 minus E0 by 2 mc square. So from the energy level, that energy difference between those energy levels, it is less than that by amount of E0 by 2 mc square for the gamma radiation. Okay. So now if you consider another case, if you are having this gamma radiation which is coming out in one case after coming this nucleus from the excited state to ground state with this much of energy difference, which is E0, and it will produce some gamma radiation. And if you have another nucleus, nearby nucleus, so when this gamma radiation comes out, it can excite one another nuclei from ground state to the excited state. Okay, so which means that the gamma radiation which is emitted from one nucleus, which is the coming out from one nucleus, that is absorbed by one another nucleus, and it is going to the excited state. That is the scenario here. So this is let's say this is nucleus 1 and this is nucleus 2. So nucleus 1 is having this gamma decay, and this gamma is coming out, and that gamma is absorbed by nucleus 2, and it is going to the excited state. Okay, so that is scenario. Now if you consider such kind of phenomena, as you can observe in the previous steps, then you will be having similar same condition, your E gamma by C, which should be equal to P nucleus. Okay, it should be P nucleus. Then your E gamma should be equal to E0 plus E recoil. Now this is the recoil energy. So why? Because in one case we are having the energy which is released, and the momentum of these two will be in the opposite direction. But when this in this condition we have momentum of the gamma radiation which is coming, which will be like this. The gamma radiation which is coming, and the nucleus is here. So when it hits in this direction, the nucleus move in the same direction. Okay, so then only the momentum is conserved. The momentum will be conserved, and in that case, our E will be equal to E0 plus ER. That is the recoil effect will be added with that E0. With that of so the total that gamma radiation energy is used for this excitation, that is E0, this excitation, as well as that recoil energy. Okay, this is having E gamma radiation, E gamma, that is energy that is coming with that of gamma radiation. When it hits on the nucleus, that nucleus has to go to the excited state, so it needs E0 energy. Okay, that is taken from that gamma radiation. Also, that gamma, when it hits on that nucleus, that will transfer some momentum to that nucleus. Then the nucleus will have some effect of recoiling. That is to conserve that momentum, and that momentum direction will be this. So since it is in the same direction, we have plus that recoil energy. That recoil energy also from that from where that energy is coming, it is also coming from this gamma radiation. So we can say that total gamma radiation is used for that excitation as well as the recoiling effect. That is E gamma equal to E0. That is energy difference between these two plus ER. Okay. In that case, where will be your spike? That will be somewhere here, that you will be getting another spectrum or another spike around this region. Okay, so you will not get a fine line because of Doppler effect, because of the nucleus, the nucleons which is moving inside the nucleus, that will form some velocity and that will cause some Doppler effect. And you can also have on Heisenberg uncertainty principle. All those things will make some fine width for these things. You will not get the 0 plus ER is exactly 1 E gamma value, and that is this line. You cannot get like that. So we will be having some fine width for that spectra, and this will be nothing but E0 plus ER, that is E0 by 2mc square, that is your recoil energy, where this ER is nothing but E0 by 2mc square. So these two spectra can be possible if you're having two nucleus. One is emitting gamma radiation, and the other one is absorbing that gamma radiation. So if both this happen, then nothing will observe. If one happens, then the left side spectra will observe, because when it emit that gamma radiation, you will get that energy. Otherwise, you will be having the right side one when that absorption happens. Okay. Now, if you consider any system in such a way that you do not have this recoil effect of nucleus, this recoil effect is not there. Okay, in such cases, it is possible that your gamma radiation will come out. Suppose your recoil effect is not there, which means that your recoil energy is zero. Okay, in such cases, your gamma radiation will be equal to E0, nothing but E0. So you will get a spike at the E0 position. Okay, now this can be achieved by uh, embedded system. Okay, if your nucleus is, if the nucleus is, if let's say nuclei, there are number of nucleus. If the nuclei are embedded in a crystal lattice, then the recoiling effect can be quantized. We can say it is quantized, or can be um, mm, let's say that it is not completely removed. We cannot say it is completely. We just check that. So we can the effect can be removed, or we can say, or quantized. Okay, something like that. You can check for definition for that. Okay, so if you make that nuclei in some embedded crystal lattice. Okay, if your nucleus is in some embedded crystal lattice, so that it cannot recoil by itself, the whole lattice has to take that energy. Okay, so in that case, your energy is quantized. Let's say some this zero, after zero we'll be having some. For example, I say For example, if you are having some X energy, okay, if some X energies are coming, then only it can take that energy. Then next time it will become 2X, then only it will take that energy. Otherwise, if it is 3X, it will take that energy. So it will not take any values in between these things. Okay, only X, 2X, 3X, those energy it will take. When you are embedded your nucleus in a crystal lattice, the whole lattice has to take that energy. The nucleus itself cannot take that energy. In that kind of situation, your energy is quantized, and if this gamma radiation is coming and hitting this nucleus, for example, so or if it is leaving from this nucleus, so the nucleus will not recoil, because the lattice will not allow it to recoil, because this whole system is now quantized, is having some quantized energy state, which means that it will not absorb any energy which is less than X, which is less than 2X in between these two. So any energy which is coming in like a classical picture, any energy which you cannot give, it will not absorb, it will not give out also. So if gamma radiation is coming out and the recoiling is needed some energy which is less than X, it will not recoil because the quantization of energy is there. So that will not accept any energy which is less than or in between these quantized levels. So if you embedded that, if you use that nucleus which is embedded in a crystal lattice, then the whole lattice has to take that energy. Now your energy is quantized, so it will not give you energy which is less than that quantization value, which is in between that quantized values. It will not take energy in between those values. It will take only values which is in the quantized form. So if the recoiling energy is happen to be in between 0 to X or X to 2X, anywhere in between these energy levels, then that energy will not be taken or will not be given by the nucleus in such a way that you can make your recoil effect become zero. In such cases, you can have a spike at E0. You can have a spike, and normally this will be not that much of that this spikes, which is for these two case absorption emission. This spikes will be larger, and this is smaller because a few nucleus only will have this kind of nature. So if you can embed it, if you embed your nuclei, if you put your nuclei in an embedded in a crystal, ഒന്നുകൂടി ഞാൻ പറയാം. അതായത് നമ്മൾ രണ്ട് കേസാണ് കൺസിഡർ ചെയ്ത് ഇവിടെ ഈ കേസിൽ ഇപ്പോൾ ന്യൂക്ലിയസ് അത് ഗാമ ഡീകെ ചെയ്ത് ഗാമ ഡീകെ നടന്നതിന് ശേഷം ആ ഗാമ ഡീകെ വെച്ചിട്ട് നമുക്ക് വേറെ ന്യൂക്ലിയസ് അബ്സോർബ് ചെയ്യാം ആ ഗാമനെ, എന്നിട്ട് അത് എക്സൈറ്റഡ് സ്റ്റേറ്റ് പോകും. അപ്പൊ അങ്ങനെ നടക്കണം എന്നുണ്ടെങ്കിൽ മിനിമം നമുക്ക് E0 പ്ലസ് E0/2mc², ഈ എനർജി വേണം. ഓക്കെ, ഈ എനർജി ഉണ്ടായി കഴിഞ്ഞാൽ എങ്ങനെ ഒരു അബ്സോർപ്ഷൻ നടക്കുള്ളൂ. ദാറ്റ് ദി ഗാമ വിച്ച് ഇസ് കമ്മിങ് ഔട്ട് should have this much of energy. അത്രയും എനർജി ഉണ്ടായി കഴിഞ്ഞാൽ അബ്സോർപ്ഷൻ നടക്കുള്ളൂ. കാരണം സം പോർഷൻ ഓഫ് ദാറ്റ് എനർജി ഹാസ് ടു ബി യൂസ്ഡ് ഫോർ എക്സൈറ്റേഷൻ ആൻഡ് സം പോർഷൻ ഹാസ് ടു ബി യൂസ്ഡ് ഫോർ ദാറ്റ് റീകോയിലിംഗ് എഫക്ട്. അപ്പൊ ഇത്രയും എനർജി ഉണ്ടായി കഴിഞ്ഞാൽ മാത്രമേ അബ്സോർപ്ഷൻ നടക്കുള്ളൂ. അതുകൊണ്ട് ഈ സ്പെക്ട്രത്തിന് നമ്മൾ വിളിക്കുന്നവരാണ് എനർജി നീഡഡ് ഫോർ അബ്സോർപ്ഷൻ. ദാറ്റ് വിൽ ബി ഗിവൺ ബൈ ദിസ് സ്പൈക്ക്. ഓക്കെ, എനർജി നീഡഡ് ഫോർ absorption, that is resonant absorption, and this particular absorption is called as resonant absorption, that the gamma decay which is produced by one nucleus and that particular radiation is absorbed by nearby nucleus. Such absorptions are called as resonant absorption, and that gamma radiation should have the energy E0 plus E0/2mc² in order to achieve that resonant condition. And secondly, what we discussed is that recoilless emission. Recoilless emission on other, if the nuclei are embedded in a crystal lattice, then the energy will be taken in quantized form. If the recoil energy which is less than that the quanta of energy, then that energy will not be taken by the nucleus, or it will not liberate, it will not give that energy out also. So in such cases, we will not have any kind of recoil effect. if you put your nucleus in a crystal lattice, you bound that nucleus in a crystal lattice, then that whole lattice and the nucleus has to take the energy, and the energy is quantized now. If the recoil energy is less than that quantization value, then that recoiling effect can be neglected. Then you will get a recoilless emission for that gamma decay. Okay, which means that full energy will be taken away by the gamma radiation. There is no recoil effect. So from that we can understand what is the excited state to ground state energy difference also by measuring that gamma radiation energy that is coming from that recoilless emission, that will be having that full energy, that is nothing but the energy difference between those excited state and ground state. This energy, that full of that energy is taken away by the gamma. There is no recoil. So we can have an estimate between how much energy is there for this excited and ground state energy levels. And that kind of an emission is called as recoilless emission, and that will be given by this spectra at the center. And this spectra will be smaller because number of nucleus which will give you recoilless emission is very small. So that's why it is small as compared to these two cases. And if you have this much of energy, you'll be having that absorption, resonant absorption. And the gamma, this spike is coming from the energy of gamma after decay, because some energy will be taken away for recoil effect. So E0 minus E0 by 2 mc square will be the energy of the gamma decay. That is given by this particular case. So that's all about